So we've made it to the end of the semester. Your last homework assignment is due tomorrow by 12 o'clock. We'll go over a couple of examples and illustrations during today's class that will help you with the last two problems on that assignment. The next thing that you'll have on your schedule then will be our final exam, which is a week from today, from 11:15 until 12:15. And so that's going to be here in this same classroom location. And the exam is comprehensive, meaning that you can have any question that you would have seen earlier in the semester, although generally I have more of the points drawn on the material since you've been tested last. And so there will be, a disproportionate number of the points earned from energy, grade lines, pumps, the material that's covered in Chapter 7. I'm going to give you the same formula sheet that was available for the first two exams, so there won't be any surprises there. Since we have 120 minutes for the test rather than our previous time limit of 75 minutes, that's going to give me the flexibility to ask more questions than I otherwise could. And the advantage of that is just that then if you happen to be rusty on one particular thing, it doesn't have a huge impact on your grade if you make a mistake on one problem type. So I hope that the exam will have a pretty broad diversity of questions just to give kind of a holistic view of what you learned and retained through the semester. So if you have any questions as you're studying for the exam, please feel free to stop by my office or send me an email. I'll be in the office much of next week. I think the suggestion on a good way to prepare for the exam is that if you haven't already, take the time to go through the solutions that I have posted for each of the homework assignments. I know that when you have just another assignment coming up and so many other classes, sometimes you don't take the time to reflect on how your assignment maybe was right and how it was wrong. So on any assignment you didn't get full credit on, go through the solution that's posted on MU Online, and so that's one study suggestion. The other is if you haven't been reading along with the textbook, it has a lot of really useful descriptions, and that second point of view can be helpful when you're standing at the end of the course and kind of have now a whole view of all the information we've covered. The secondary point of view can maybe make things click in a way that they haven't so far. And of course, the lecture recordings is just another resource that you've got available. If you read through an example that we worked and you don't quite remember what was the process or the technique or the justification, I wouldn't advise going through the entire lecture, but I mean you can skip easily enough to the examples and maybe refresh your memory on how some of those worked. So those are the announcements from here on out. Any questions so far? Yeah.
Is the exam hours 10:15 to 12:15? You said 11:15.
Did I say 11:15?
Yeah.
Yeah, it's from 10:15 until 12:15.
Just making sure.
Mm-hmm. Are there other questions? Okay. Well, we are working with the energy equation and talking about pumps and generators, and so you have a problem that's similar to this on the homework assignment, and I thought we'd take the time to address what if we have a pump that's providing the power to lift water from a source tank up to a residential area and then beyond. In this problem, we know a given flow rate that we want to achieve. Sometimes in piping and pump problems, you know what the specifications of the pump are. So sometimes, for example, you know how much pump head is being added or what's the power of the pump, and you want to find out what will the flow rate be as a result of the energy that's available and the resistance to flow that exists in the pipe. This is looking at things a little bit differently. This is saying that we know that we want to achieve a certain flow rate through the piping, and so we're asking the question, how much energy has to be provided by the pump in order to achieve that target flow rate? So in steps A through C, what we're doing is we're kind of looking at step by step. First of all, how much energy has to be added by this pump in order to overcome the local losses, which are an inlet loss. And the previous inlet loss that you saw, the K value was 0.5 because the pipe was flush with the tank. If you go into the local loss tables, you'll see that if the pipe extends into a tank, then there's more energy loss associated with that, and so as a result, the K value of 1 is used when you have an entrance where the pipe extends into the tank like it does here. So we've got a K value of 1 there, a bend that gives us 0.4, another bend of 0.4, and so any place we have the same pipe diameter, like we do here, the entire pipeline is 500 millimeters, then you can just add up the K values. However, if you had different pipe diameters, let's say for instance if this inlet pipe was large and then the outlet pipe from the pump was a smaller diameter, then you'd have to treat these K values separately. Because remember, the formula for local losses, H naught, is K times V squared divided by 2G. So the local loss is dependent on the velocity head at the location that the local loss applies. So if you had a large diameter pipe, there would be one velocity for the inlet loss. But then if we had a discharge pipe with a smaller diameter, then you'd have a different velocity at this bend and at the other bend. And so you'd have to separate the K values rather than just adding them all together. Just wanted to let you know about that wrinkle that sometimes can pop up. In our case, you'll be able to add the K values for the local losses because the pipe diameter is the same through the entire distance. And so what we know is that from this inlet to the discharge that's shown is 2,000 meters. And so applying the energy equation, our strategy is always pick location 1 and location 2 to be spots where we have lots of information, because there's going to be enough unknowns in the equation already without picking a spot where we don't know the pressure or we don't know the velocity, for example. And so the typical thing that we've done in the past and is appropriate here as well is to pick the surface of the reservoir as location 1 and then the outlet of the pipe as location 2. And for whatever reason, this pipe terminates at a free discharge. It maybe is dumping into another storage tank downstream, but what we know is that it's atmospheric surrounding the jet of water, but the water is retaining its velocity head. So when you're applying the energy equation, location 1 is at the surface of the origin tank. Location 2 is at the jet of water that comes out of the pipe. And so between 1 and 2, you have to look and see, is there a pump? Is there a turbine? And what are the losses? In order to ask yourself, the unknown here, H sub P, we're trying to find out what is H sub P in the energy equation. And then once you know the pump head required, substituting that into the power equation, where it's the flow rate Q times the unit weight gamma times H sub P, and then where we're finding out the electrical power that has to be added. Remember, last time we looked at a turbine, and we said that in the case of a turbine, you multiply by the efficiency factor because you get less electricity out of the turbine than the power that's put into a turbine. In this case with the pump, I'm not going to come right out and say it. I want you to remind yourself what you need to do in the case of the efficiency factor, whether it's multiply or divide. But I'll pause for here and give you some time to work through the calculations of when we know the friction is described by this relationship. We have a given F value, in other words, for the Darcy-Weisbach equation, which characterizes the roughness of the pipe. Remember, the pump is being added to overcome three things. The pump is adding enough energy to lift the water because of the delta Z. The pump is also overcoming the effect of the local losses, and it's overcoming the resistance effect of the pipe friction. So the amount of pump head that's added, H sub P, depends on those three things. So when you're working on part C, the thing that you need to take away from the drawing is that all of the local losses are before the house. So those still apply, but the frictional losses are less because you only have a fraction of the pipe length prior to the house. What I assumed when I was solving this is that there's zero velocity head. You know, the water is coming up into a pipe and it's terminating inside the house under static conditions. The water is just in the faucet, but the faucet isn't on. We want to know what's the pressure under static conditions at the top of the building. The solution to part A is up on the screen right now. If you're really a stickler for precision and you put the alpha into the velocity head, the 1.05, then instead of 0.44 meters, that's 0.46 meters. So then that would change the final answer to 50.46. But that kind of illustrates why in a lot of cases people don't bother to keep track of the kinetic energy correction factor of alpha equals 1.05 because it has such a minor effect in the end. But the pump has to add enough energy to overcome the lift. So the delta Z's is the lift that it's doing. Has to add enough energy so that we still have velocity head, you know, to start moving the water because it was stationary in the tank, and so you're requiring energy to take it from stationary to moving, and that's what this 0.44 meters of head is for, is giving it the kinetic energy. And then the local losses that are being overcome, 0.8 meters, and the frictional losses that are being overcome, the 33.8 meters. For a 2,000 meter section of piping. So this has got to be a pretty strong pump, 50.44 meters. So what you'll do then is take that pump head and put it into the power equation, and of course we're having to divide by the efficiency factor, because if we need to add a certain amount of power to the water, then the electricity required is going to be even greater than the power that makes its way into the water because of the losses to heat, vibration, light, and so on. Okay, so how much electricity are we consuming with this 58% efficient system in order to get the water through the pipe, lift it up, still with a little bit of velocity head? So if we're adding 50.44 meters of head, then the power requirement is going to be 495 kilowatts. That's a lot of power. But of course, it's a really high flow rate too. So that's how we would incorporate the power calculations once we've calculated the pump head. Now the question is, so we've got that system in place. The pump is big enough to move the water through the pipeline, but if we have this spur line, like a secondary pipeline coming off, a lateral pipe that's in the building, and the elevation of the pipe goes as high as 102.69 meters, then what would be the pressure there? So we neglect any losses that are after, because we're asking the question essentially, how much energy is in the water at this point that's before the end? I mean, we know how much energy is in the water at the end. At the end, the energy is simply the elevation and the velocity head. We've added a bunch of energy with the pump, so how much is left by the time we go 1,100 meters downstream? And we want to know the pressure in terms of, the energy in terms of the pressure that's available. All right, so going back to the energy equation, now we're substituting into the energy equation where we're going from the water tank to the to the building, so we don't cancel out the P2 term. That's the unknown that we're trying to solve for, is the pressure in the building. So the H sub F isn't going to be the same head loss as it was before because the length is different. Instead of 2,000 meters, we just have 1,100 meters. So we're only losing 18.59 meters of head due to pipe friction, but the local losses are the same. So we should have pressure of 56 kilopascals. Did anybody else get roughly that same pressure value? Okay, I'll leave it up for a minute in case you need to copy some things down or take a look. Now, a typical municipal guideline is that a minimum water pressure during an emergency, it's okay for the water pressure to go as low as 140 kilopascals. Under typical kind of standard day-to-day operations, they'd want around 240 kilopascals. And so this is much too low. And in a case like this, probably what the utility would be forced to do would be to order a boil water advisory. And the reason for that is that when the pressure falls below 140 kilopascals, there's a risk of backflow. You know, backflow being where if you had a submerged pipe and there's like water in a bathtub, it could back into to the distribution piping and contaminate the water there. So for sanitary reasons, they usually set 140 as the lower threshold, and this is too low, just for a basis of comparison. But that's the pressure we'd have. So if we wanted to achieve 240 kilopascals at that building, then we'd need a bigger pump. So that's, you know, setting this to 240 and putting it back into the energy equation, we could solve for what is the H sub P required to give us that desired pressure, if that was the way that we were looking at things. Okay, so any questions on this example? Now that we've worked on it, I think that you'll find the corresponding homework problem to be pretty straightforward. The only complicating factor is that in the homework problem, it's traditional units. So the power equation, where we've been doing it in SI units, I just wanted to reiterate that if we have the flow rate in cubic feet per second and the unit weight of the water expressed in terms of pounds force per cubic foot, so the typical unit weight of water is 62.4 pounds of force per cubic foot, and then the pump head is in terms of feet, then you'll get power from this power equation in foot-pounds per second, and there's 550 of those in a horsepower. So this problem is asking, you know, essentially, how much energy does the pump have to provide in order to lift the water at a certain known flow rate, where we know that there's going to be losses that increase as a result of that flow rate. So for this problem, maybe the thing to keep in mind is that once you've found the power in foot-pounds per second, just divide by 550 to get horsepower. In this sketch, they've mentioned the elevation of the pump. Does that matter?
Yeah.
I mean, I guess it depends on how you look at it. It doesn't matter to find out the power that has to be provided, but it's generally useful to know the elevation of the pump because it helps you to keep track of cavitation risk. So this is a pretty long suction side, 1,000 feet of pipe. As a general rule, they would try and keep the suction side pipe length to a minimum because it's before the pump that the pressures get the lowest. If we think like what's happening to the pressure of the water in this situation, well, when the water first goes into the pipe, it's got a fair amount of pressure because there was a good height of water inside the tank. You know, 90 feet of elevation, and assuming this is a horizontal pipe, the pipe elevation is at 40 feet. So we've got 50 feet of pressure. You know, if we think about pressure in terms of a distance, there's 50 feet of pressure head here in the pipe, but then it's decreasing because of pipe friction. And so the pressure is high, but the pressure is getting lower, and the pressure is getting lower. And so the question is, if the pressure goes below the vapor pressure, then cavitation can occur. And so that's kind of why, in a lot of cases, when you see a problem like this, they will tell you the elevation of the pump, because then you could have a cavitation type problem built in. There isn't one in your homework, but so the pressure is getting lower and lower and lower. What happens to the water pressure once it hits the pump?
Does it increase or?
It does increase. Think about a pump is adding energy, and there's three places that the energy is. You know, the energy exists in the pressure head, the elevation head, and the velocity head. So think about the water before the pump versus the water after the pump. Let's assume that, not assume, it says right in the sketch, 8 inches in, 8 inches out. So the diameter is the same. So how is the velocity of the inflow compared to the velocity of the outflow?
They're practically the same.
They're the same. If the pipe diameter is the same, then the velocity in and the velocity out have to be the same. That's continuity that tells us that. Q in equals Q out if there's no capacity for storage. And this isn't a storage tank, it's a pump. So the pump isn't adding energy in the form of velocity. It's not like the velocity out of the pump is higher than the velocity in. So it can't add energy in the form of velocity. Now, this pipe is inclined, and so over time it's gaining elevation, but just right on the outside of the pump, the elevation is the same. The inlet and the outlet elevation is the same. And so the pump isn't lifting the flow. Some pumps do that. Positive displacement screw pumps, which are open to the atmosphere, can add elevation. But those are kind of rare. Those are like a novelty. An enclosed pump like this adds energy by increasing the pressure. And so instantaneously what happens is, remember, the pressure was getting lower and lower and lower just because of pipe friction. And then suddenly the pressure is boosted instantaneously much higher, and then the pressure starts going down again as we get further and further downstream. So that effect of a sudden increase in the pressure is something that we're going to see when we start talking about hydraulic grade lines and energy grade lines in a little bit, in just a minute. Before we get to that, I wanted to tell you a little bit more information about the Darcy-Weisbach equation, because in the examples we worked so far, like this one, it just has the friction factor 0.018. And this example, 0.019. Like that was given, and I wanted to tell you where numbers like that come from and what it takes to know the friction factor. And so the place that you start when you're estimating or calculating the friction factor is understanding how rough the pipe is. And different types of materials have a different inherent roughness to them. Smooth pipes like drawn tubing or glass have a roughness that's very, very low. And the epsilon value here in millimeters is expressed in terms of what they call an equivalent sand roughness. And so what that means is that they're looking at the irregularities in the surface, and they're trying to express it in terms of if it was the same effect as a sand grain, what would be the diameter of that sand grain. And so here they're saying, just as an example, in a galvanized iron pipe, a new galvanized iron pipe that doesn't have corrosion or mineral deposits, just the irregularities in the surface having to do with the grains of the iron and the crystalline structure of the material, that has an equivalent sand roughness of 0.15 millimeters in diameter. So if we were just to look with a microscope at that material, if you zoom in on the pipe, it kind of looks like this. You know, it's got some average roughness to it. And if we instead had a perfectly smooth pipe, but then we glued sand grains to try and approximate the irregularity of that crystalline structure in whatever the material is, then we're essentially trying to find out what would the diameter of that sand grain be to have the equivalent effect. And so certain materials like a rough concrete that hasn't been smoothed or finished with a lot of care can have a equivalent sand roughness of up to 3 millimeters. You'll notice that corrugated metal pipes, which are often used in culverts and with roadside ditches, because of the corrugations, they have a very high equivalent sand roughness, even though material itself is just steel. It's usually galvanized steel. But because of the corrugations, it has a much larger roughness. So the first thing is a problem where you're trying to find the friction factor F will tell you what the pipe is made out of. So you'd have to know the roughness, and then you would go to what's known as a Moody diagram. And this is a graphical way of estimating the friction factor F. And this is kind of a classical figure that is really important in engineering, at least in the hydraulic design and fluid mechanics side. If you go through the FE reference manual, you know, the formula equation that they give you for the FE exam, this figure is in there prominently. It's an important one. What it does is you start on the secondary vertical axis on the right-hand side of the figure. What it says is the relative roughness. And so it's the equivalent sand roughness relative to the diameter. So for instance, if we have an epsilon, sometimes like in the following figure, the relative roughness has the variable k sub s. Sometimes it's called epsilon, sometimes it's called a k sub s, but it means the same thing, the equivalent roughness. So let's say that you have a concrete pipe that is finished smooth. So the equivalent roughness is 0.3 millimeters for that smooth finished concrete pipe. So if epsilon is 0.3 millimeters, and if the diameter of the pipe is 300 millimeters, then epsilon to diameter is 0.3 divided by 300. So what is that? 1,000? So in this vertical axis, they have the equivalent relative roughness as the vertical axis. And so we would use the point 001. And then you'd have to know what is the flow conditions going through that pipe, because the F value kind of considers how thick the boundary layer is going to be where there's laminar flow conditions. And it has to do with the velocity profile. When water is going through a pipe, remember that if we have laminar conditions, there's kind of this bullet-shaped velocity profile where the velocity is the fastest in the center of the pipe and the slowest at the edges. This is if we have laminar conditions. If the conditions are turbulent, it looks a little bit differently. It would start at 0 at the edge of the pipe, but it would quickly go up, and then there's a lot of random variation, and then it goes back down again. So the reason why we have to know the Reynolds number of the flow through the pipe is because we're trying to figure out how thick is this section right here where we're going from 0 flow rate up to the average flow rate. The thickness of that region where there's a low velocity is really important because the roughness of the elements in the pipe are either going to be sticking out into that turbulent zone. So the roughness elements in the pipe, the question is the sand grains going into the turbulent zone, or is it fully inside that laminar cushion where the velocity is low? So to find out the F value, what you do is you calculate the Reynolds number in the pipe, and you follow this curve of the relative roughness to intersect with whatever Reynolds number you determine, and then you go over to the primary vertical axis on the left side, and then that's how you get the F value. So it's the intersection of these sloping relative roughness curves with the Reynolds number, and then to the left to get the F value. Now, you'll notice that there's this dashed line, and there's a region of high Reynolds numbers where the relative roughness doesn't depend on flow conditions. And what that means is that once the velocity gets really high, that it no longer, if you increase the velocity in the pipe so that the Reynolds number goes from 1 million to 10 million, that's not going to affect the F value once you get into what's called the rough turbulent zone. But below that rough turbulent zone, in this transitional zone, then the friction factor F depends on both what is the Reynolds number and what is the relative roughness. So we'll spend a little bit of time next semester in 331 revisiting the Moody diagram, and there are some equations that approximate it. But I wanted to give you an idea of where this F value comes from and what makes the Darcy-Weisbach equation so accurate. The reason why Hazen-Williams isn't as accurate as Darcy-Weisbach is that Darcy-Weisbach equation has an F value that depends on flow conditions. So imagine in your case, when you've already seen how the Hazen-Williams equation performs, what if you had a different C value for low flow rates compared to high flow rates? And what if you had a different C value for small diameter pipes versus large diameter pipes? That's essentially what's happening here. You're taking into account both the pipe diameter and also the flow conditions when you pick what is the roughness value, F. And so F is a lot more specialized to actually what's happening inside of the pipe, and that's why we get so much more accuracy out of Darcy-Weisbach equation than we can out of the Hazen-Williams equation when we want to estimate the effective pipe friction. So any questions about the Moody diagram? Okay, so the last thing we're going to do today is take a look at how do we visualize and in a graphical way describe what's happening with the energy in the system. So here's a sketch that shows a pipe that's connected to a tank. And the definition of energy grade line and hydraulic grade line. We've already talked about just a moment ago where the energy can be in a system. Energy can exist as potential energy or kinetic energy. So potential energy is the pressure head and the elevation head. Those two things together, the hydraulic grade line is the potential energy in the system, and then the difference between hydraulic grade line and energy grade line is the velocity head. So you can see a sketch of both, and in this case they're parallel. These two lines are parallel because the energy is decreasing in the direction of flow at the same rate. It's decreasing because of pipe friction, and the pipe friction affects both the EGL and the HGL at the same rate. Now, on the left-hand side of the sketch, inside the tank, the indication is that the HGL and the EGL is at the water surface. And so the energy inside of the tank exists only as the Z. If we look at these three terms, pressure head, elevation head, and velocity head, there's no pressure in the water at the surface of the water. And it's such a big tank that it doesn't have any velocity. Even if water is going out, it's falling so slowly that the velocity head is negligible. And so all of the energy exists as elevation inside of the tank. So you can see that once the water gets into the pipe, it's accelerated, and it's gone from stationary to now having motion. And so there's now a divergence, whereas previously the EGL and the HGL were on top of each other right at the water surface. Now the HGL is below the EGL. And the distance between them, that gap distance, is the velocity head. And so the vertical deflection between the EGL and the HGL is just dependent on what's the velocity through the pipe. So you can actually physically see the HGL with the piezometer. And you have seen the HGL before. When we did the Bernoulli lab a couple of weeks back, we had those tubes that were going up from the Venturi. And those tubes were just basically a puncture in the top of the piping. They weren't where the flow was directed so that there'd be a stagnation. If there's a stagnation tube, then the water will rise a little bit higher because of the velocity head that's terminating at the opening of the pipe. And so here you can see the EGL. If you wanted to physically observe that, you'd have to have a stagnation tube where a streamline was intercepted by the opening of a tube that's facing in the direction of flow. At the end of the pipe, the EGL stays above this jet of water just a little bit because this jet of water that's coming out still has some residual velocity head. And so the energy that's in the water is the pressure, the elevation, and the velocity head. And so it's the water's location plus a little bit of extra deflection above the water surface to account for the velocity head. Now my opinion is that they're a little bit sloppy. They should have terminated that line where the pipe itself terminates. I keep every year wanting to revise that figure because if I had drawn this sketch, I would have had the HGL stop right at the opening of the pipe because the HGL represents, with the horizontal pipe, how much pressure is inside of the pipe. And so it loses its pressure right at the opening, not prior to the opening. But I mean, besides that, it's a good figure that illustrates what happens when water is flowing through a pipe. The pressure is decreasing, and these EGL and HGL sketches are really important in the design of a lot of different systems. It's like, for instance, in a water treatment plant, if you have the design drawings of a water treatment plant, oftentimes they'll have the HGL and the EGL marked up because as much as possible they want water to be flowing through treatment plants by gravity so that there don't have to be lots of pumps that are consuming electricity, and so they'll be pretty thorough in sketching how much energy is in the water, not just where is the pipe, but how much energy is in the water that's flowing through the pipe so that as much as possible they can have it be a gravity flow system. This is what I described as the effect of a pump, how it instantaneously adds pressure, and so the EGL and the HGL both will go up, and this is a vertical line, and then the energy continues to decrease once the water exits the pump, is now in the pipe. It's losing pressure due to pipe friction, so then these are both sloping downward. Here's how a turbine affects the system. It's kind of you can think of a turbine as the inverse as a pump. Whereas a pump instantaneously adds energy, what a turbine would do would instantaneously remove pressure from the system. And so you can see that this is sloped downward because we have energy loss as the water is flowing through this from the elevated tank through the penstock towards the turbine. But then the turbine is using the pressure on the upstream end of the penstock to force those turbine blades to spin. And there's resistance there. You know, the generator is providing resistance to the turbine blades, but the reason why there's the energy to do it is because the turbine is taking a high pressure liquid and discharging it to a low pressure receiving body. And so in terms of the HGL and the EGL, it's just an immediately a vertical drop down. Now the EGL and the HGL are getting closer together. If you look at, they've put a little bit of nuance into this sketch that I think is interesting. The diameter of the pipe is increasing, which is pretty common if you don't want to have a big jet of water to scour the bottom of a reservoir or a river. So let's say one reason why you do this, why you have a gradually increasing pipe, is that flared diameter is reducing the velocity so that there isn't scour, if this was like an earth channel downstream. And so because the velocity is decreasing, then what that means is the gap distance between the EGL and the HGL is getting closer and closer together. And so that's one thing I want you to note, is that they're parallel as long as the pipe diameter is constant. But then when the pipe diameter is increasing, the EGL and the HGL are no longer parallel. And that same effect is visible here, where the decreasing diameter causes a divergence in the EGL and the HGL. So whereas before they were pretty close together because there wasn't much velocity head, now as the velocity increases, then the velocity head increases a lot because velocity head is dependent on velocity squared. So now there's a big gap between the EGL and the HGL because the difference between the two is velocity head. And for a moment here, before it discharges into the jet, you'll notice that the EGL line also became steeper. And the slope of the EGL line is a reflection of the rate of energy loss. So the fact that this is a little bit steeper momentarily is the author's attempt to illustrate the fact that head loss increases when the diameter decreases. That same effect is shown in this sketch, where the smaller diameter pipe has the steeper EGL. So the slope of the EGL is the rate of energy loss due to pipe friction. And so when you have a big pipe that's feeding into a small pipe, the things to note is that the slope is steeper for the small pipe, and there's a larger gap distance between the EGL and HGL because if you have a higher velocity, then there's a larger velocity head. And as they pointed out here in the dimensioning, v squared divided by 2g, that's the magnitude of the gap between the two. Now the sketches that you do don't have to be to scale. They're just kind of conceptual and qualitative in nature. So I'm going to hand out a piece of paper for you to get some practice doing these sketches, and you don't have to make it a scale drawing where the gap distance is exactly referring to how much velocity head there is. Instead, what I'm looking for is just that you illustrate these same trends, that if you have a large diameter pipe, that the slope of this line is relatively shallow compared to a smaller diameter pipe would have a steeper slope. One last thing to point out is that the HGL terminates at the water surface because that's where you're getting to zero pressure. The HGL, remember, is if you punctured the pipe in a piezometer, how high would the water level rise? And so by the time you get to the tank, the pressure should be equal to the elevation of the tank itself. But you lose the velocity head. Do you remember the K value for an outlet is 1.0? And so what that means is when we have a K value of 1.0 for the local loss, when a pipe is discharging into a tank like this, it means that all of the energy that was tied up as velocity head just kind of dissipates into the flow. And so that's why the EGL terminates above the water surface. They're indicating here the head loss at the outlet. You're losing the velocity head as head loss. The purpose of this sketch is to illustrate that the physical elevation of the pipe does not affect the location of the EGL and the HGL. That the grade line depends on the energy loss characteristics of the pipe. So the slope, the downward slope of this is not affected by the fact that the physical location of the pipe is going up and then going down again. Remember that the EGL and the HGL is the sum of three terms. It's the sum of the pressure head term, the elevation term, and the velocity term. So this constant diameter pipe, the velocity isn't changing because it's wiggling around like that. It's the same diameter everywhere. But what's happening when the pipe is going uphill, you're gaining Z and you're losing pressure head. But the net difference is that there's no loss in energy just because the water is going uphill. It's just an exchange in where the energy is. It's exchanging some pressure head for elevation head. So what happens is that the EGL and the HGL continue downward just at a rate that's dependent only on the friction loss characteristics of the pipe. Whenever the pipe is above the HGL, so this dashed line is the hydraulic grade line. And remember, if we punctured the pipe and we connected a tube, the water is going to rise to the level of the HGL. So if we if we put a hole in the pipe here, water's going to spray out. And so we connect a tube, the water's going to rise up to the HGL. But what happens if we puncture the pipe here? When the physical location of the pipe is above the HGL line, if you puncture it, rather than water spraying out, air would suck into the system. Sometimes this is called an inverted siphon. When you have the physical location of the pipe is above the HGL, it would actually have a suction effect. And so one of the things that we could ask ourselves is, well, is the negative pressure in the pipe below the vapor pressure of the fluid? And if it is, then you could potentially have cavitation in a location where the pipe is above the HGL. So with that, the key points, remember, is that when you have an inlet to a pipe, the EGL and the HGL diverge, that the EGL and the HGL should be parallel with the distance between them corresponding to the velocity head, and then at the discharge end, if it's going into a tank, the HGL terminates at the water surface and you lose the energy head if it's going into a tank of stationary water. But if it's a jet of water, then the EGL stays above the water surface. All right, I have a handout for you to get its front side and back side. I'd like you to get some practice sketching the EGL and the HGL, and I suggest that you use pencil. That sometimes with these, you need to erase your first attempt. It can be an iterative process of figuring out where to start and where to finish, especially when you've got a local loss or where you've got a pump. And on this one, you're going to have a local loss, the one that I've handed out, at the junction of the small pipe to the large pipe. Okay, so let's talk about what we need to illustrate in this one. So the smaller pipe is going to have a larger velocity. So the EGL and the HGL should be further apart for this one. Compared to the larger pipe, the velocity will be lower, so there will be less of a gap between EGL and HGL. And then the other thing is that the slope of the line should be steeper for the small diameter pipe because we're losing energy at a greater rate. So you know there's going to be a downward slope having to do with energy loss, and it should be a steeper slope for the small pipe compared to the large pipe. So let me show you what the solution for that should look like. The sketch should be something like this. Now, how far offset it is here, I'm representing a local loss. And by the way, your sketch looks a little bit different than this one. I compressed it just to get it to fit on the screen. But the point is that the two lines should be parallel. They should be further apart for the small diameter pipe compared to the large diameter pipe. So you notice the big gap distance here, small gap distance, and then there's this drop down having to do with the local loss. The connection of this pipe here, the expansion, is there's going to be a K value associated with that. So there's a localized reduction in pressure having to do with the transition. Now how big? It doesn't necessarily, you know, everyone's interpretation and scale is a little bit different, but what we do know is that this can only be sloped downhill. It can't be sloped uphill, and it can't be flat. It can only be sloped downhill. And then the slope of this is less because the pipe diameter is larger. And then the EGL should terminate above the water surface. The HGL should terminate below the water surface. At the water surface. Okay, so flip the paper over, take a look at that. Give it 1 minute's worth of thought, and then I'll show the solution just to see if we agree.
Cavitation. It goes from small to big.
All right, I've got my sketch up on the screen where what we have is the water is losing energy as you move in the direction of flow. It's always going to be going downhill, and then a sudden increase in energy. And well, this is not my best sketch because it looks like those lines aren't as parallel as they ought to be. That's unintentional. But what we do see is that the slope is steeper here because it's a small pipe compared to a large diameter pipe. The gap distance is greater for the small pipe because we have a larger velocity head. And then it terminates at the water surface for the HGL and above the water surface for the EGL. Okay, well, we're out of time, 12:15, so the last thing that we have is the final exam. I'll see you next week for that, and if you have any questions in the meantime, feel free to stop by.
Well, I'll be seeing you twice that day for the eco and the fluid.
That's right.